Hello everyone, and thank you for being here today. Myself, Rohan Jain, and in this presentation, I'll walk you through my project where I used machine learning techniques, rather smart computer techniques, to predict diabetes risk using real patient health data. We'll see how technology can not only improve our understanding of health data, but also help us make life-saving decisions faster. By the end, you'll see how even simple models, when used thoughtfully, can make a real impact in healthcare. Diabetes is a chronic disease where the body cannot regulate sugar levels properly. Over time, this extra sugar quietly damages the heart, kidneys, eyes, and nerves. It's often called a silent killer. The reason being, many people don't even know they have it until the damage has already begun. Today, nearly 537 million adults will live with diabetes globally, and the number is rising rapidly. Early detection is crucial, but sometimes early signs are hard to notice. That's where the computers can help. They can find hidden they can find patterns hidden inside complex data, patterns humans might overlook. The goal of my research was simple: use basic health information to predict if someone might be at risk of developing diabetes. Health indicators like blood sugar levels, body mass index, also known as BMI, age, and family history were used as clues. At the same time, I wanted to go beyond simple prediction. I wanted to find hidden warning signs too. By combining both pattern discovery and prediction, this project supports patients in getting early alerts, assist doctors in making decisions, and offer researchers new path for study. In machine learning terms, I combine unsupervised learning, which is used to find hidden patterns, and then supervised learning, which is used to make final predictions. Raw versus clean data. Starting with real data was exciting but challenging, just like real life. Real data is messy too. There were missing blood sugar levels, wrong entry, and inconsistent measurements. If we didn't fix these problems, any pattern to the computer found would be unreliable. I cleaned the data like organizing a messy office before starting important work. Every missing value was filled responsibly, duplicates were removed, and all the measurements were brought to the same scale so that no feature unfairly dominated the analysis. A clean data set is a foundation of a trustworthy model, and this step made a huge difference later on. Finding the big picture, PCA. Once the data was clean, there was too much information, dozens of health features for each patient, and some features were not even relevant for diabetes detection. To simplify, to simplify this further, I used a method called Principal Component Analysis or PCA. PCA is a type of unsupervised learning which helps reduce complexity by focusing only on the most important parts. It's like if you're preparing for an exam, instead of reading tens and hundreds of textbooks cover to cover, you find a key topic that matters the most. In our case, PCA helped shrink dozens of measurements into just a few meaningful ones without losing important information. This not only made computers' job easier, but also helped visualize patient patterns better. The reason of using PCA was to make the complex calculation for each and every feature and reducing it to a low to like less features and make it more easier. Grouping the slide, grouping the similar people together using clustering. Next, I applied another unsupervised learning method called clustering. Clustering is all about grouping patients based on similarities without knowing their final diagnosis. Think about how a library organizes mystery books together and science books together in another corner. Here, patients naturally fell into groups, one group being of healthy people, another had medium risk, and the third group showed strong warning signs. This was important because it suggested that even before formal diagnosis, there are clear group patterns which we can act upon. discovering hidden patterns using ARM. Then I explored deeper connections using association rule mining, also known as ARM, a technique similar to how store knows that how people who buy milk will also buy bread and butter. In patient health data, I found that high blood sugar combined with rapid weight gain greatly increased diabetes risk. These hidden combinations were not obvious when looking at the when you look at the symptoms one by one. This means that early diagnosis, doctors should not just look at one single symptom. They should watch for groups of symptoms happening together. Finding these rules help doctor provide more personalized care rather than a one size fits all approach. Moving from finding patterns to making predictions. Once we explored and understood the hidden patterns, it was time to start supervised learning, where the computer is trained using examples with known outcomes. Supervised learning is like a teacher grading homework. We show the computer many examples, correct its mistake, and let it learn over time. By doing this, system becomes more capable of predicting nuance in patients' risk levels more accurately. In healthcare, this ability to predict ahead of time is what makes machine learning truly powerful. Technically speaking, we use label data on which we train our model to find out whether a given patient has diabetes or not. How did how well did simple predictions work using Naïve Bayes? Naïve Bayes being one of the most simplest prediction model and a quick learner worked by checking one clue at a time and assuming all clues are independent. Even though it's based on a very basic idea of choosing one clue at a time, it performed surprisingly well, achieving 82% of accuracy. This showed that when data is prepared carefully, even simple models can deliver strong results. Simple doesn't mean weak, especially in healthcare, where fast, interpretable results matter a lot. Decision trees. Next, I tried building decision trees, system that asks a series of yes or no questions to predict outcomes. For example, is your blood sugar above a safe level? If yes, then go down one branch. If no, go down another. Initially, the trees were perfect, but after carefully tuning how questions were asked and structured, accuracy rose to nearly 89%. Decision trees are valuable because they provide transparent reasoning for both patients and doctors to understand exactly how a prediction was made. Simple lines work the best using logistic regression and SVM. I also tried simple boundary methods like logistic regression and support vector machine. These models try to draw a straight line between healthy and risky patients. Although I could have used fancy curves or complex transformations, simple straight line boundaries actually performed better. I used polynomial and RBF SVM, but out of those, simple linear SVM outperformed both. This teaches us a big lesson. In real world problems, especially healthcare, clarity and simplicity often outperform complexity. Clear decisions, easy example, and robust results were more valuable than fancy models. This random forest. Finally, I combined multiple trees using a method called random forest. Instead of trusting one decision tree, I built hundreds of small trees, each giving an opinion, and then used majority voting to decide. This teamwork approach improved the stability and accuracy of the model, reaching almost to 90% overall. It also gave insights into which health measurements were most important, like blood glucose and family history were the most important features for predicting diabetes. Random forests show that working together, many simple models combining creates much stronger and reliable results. Conclusion. In conclusion, this project showed that even with basic health measurements, computers can learn to detect diabetes risk much earlier than traditional methods alone. Careful data preparation, smart pattern discovery, and combining simple ideas led to great results. Machine learning doesn't always have to be complex to be powerful. Sometimes using simple tools thoughtfully gives the best impact. Healthcare can truly benefit from this, making early diagnosis faster, cheaper, and more accessible to everyone. Before I wrap up, I invite you to explore my full project online, where you will find detailed explanations, data visuals, all the models with code and their performance, and many more on the website. The link to the website is given in the presentation, and I'll put a link in the description as well. Feel free to browse and explore everything we discussed today. Thank you so much for listening to my presentation. I hope you enjoyed seeing how smart computer methods can make healthcare better and more proactive. Thank you.